Hello geometry students, this is Jami Emigh, and this video is our discussion on section 1.4, segments and their measure. Alright, so let's start with an example on measuring lengths of segments. They want us to find, and notice that they have capital M followed by capital P. When you see that notation, they're asking you to find the length of segment MP. Okay, so that's implied when you see the capital M next to the capital P. All right, so to find the length of segment MP, let me erase my scratch work there. You can look at the coordinates of M, which are -11, and the coordinates of P, which is 5. Okay, then you can find the distance between them using subtraction, and then the absolute value of that result. And that will give you the length of segment MP. So 5 minus the -11 is 16, and then the absolute value of 16 is 16. Congruent segments versus equal lengths. This is something we're going to have to be careful to learn. The notation is different. So here we have, if segment AB is congruent to segment CD, then you see right here, the length of AB is equal to the length of CD. So notice the subtle differences in the notation. This equal sign has a congruent symbol over it, and it's noting that it's the segment. So two segments can be congruent, but it's their lengths that can be equal, right? So let me say that one more time. It's two segments that can be congruent, but it is their lengths that can be equal. Okay, and then the vice versa of this statement is true as well. We call it the converse. If the length or measure of AB is equal to the measure of CD, then we would say that segment AB is congruent to segment CD. Look at this figure here, and using the geometric code, we can see that that single tick mark and that single tick mark is what the statement to the left of the figure is representing. Once the single tick mark is used, if a double tick mark is used in the same problem, then that would represent congruency as well. So to write the congruency statement for the double tick marks, it would be segment AD, so make sure you put the bar over top, is congruent to segment, I'm going to go CB. And it would be the length of AD is equal to the length or the measure of CB, right? So notice the difference when to use congruent is when you're talking about a segment, equal when you're talking about units of length or measure. All right, so here's our question. If BC equals 2 feet, and remember with no bar over top, they're saying that that is the measure of the length of BC, then what would AD equal? And then our second question is, if DC equals 6 feet, then what would AB equal? Let me erase some of the scratch work, and I like to put those labels right on the figure. B to C would be this segment here, and that is 2 feet. And then they're asking us for the length of A to D. Those two segments are marked off as congruent, and that means that they have the same measure. All right, let me change colors for the next one. We have DC with no line over top, so they're saying the length, the measure of the length from D to C is 6 feet. And then they're asking us to find AB. A to B is the segment that also has the single tick mark. That means that those two segments are congruent. And when two segments are congruent, we know that they have the same measure. So AB would also be 6 feet. Okay. myself I was going to be good about erasing what I wrote with my finger and then showing it to you typed in, just in case you can't read what I wrote with my finger. All right, postulate 1.4-2 is the segment addition postulate. And the postulate states that if point B is between points A and C, then AB plus BC is equal to AC. Also, if AB plus BC is equal to AC, then point B is between points A and C. So the first if-then statement and then the second if-then statement are converses of each other, just swapping the if statement and the then statement. All right, so let's look at a picture of what that's stating. If point B is between A and C, okay, here we have a point B, and it is between A and C. All right, so our first condition is met. Then we can conclude that AB, so this measure right here, plus this measure right here, BC, is equivalent to the length of the entire thing. That is the segment addition postulate. I like to just remind myself and my students that the lengths of segments can be added. 2 feet plus 6 feet, these units follow the rules of addition. So that would add to, let's say, for example, 8 feet. Okay, so when you're talking about lengths of segments, you can use addition because the lengths follow the rules of addition. So segment addition postulate. The midpoint of a segment is a point that divides or bisects a segment into 2 congruent parts. A line, ray, segment, or plane that intersects a segment at its midpoint is called a segment bisector. And here we have a visual so I can talk about each of those definitions. All right, so first one, a midpoint of a segment is a point that divides or bisects a segment into 2 congruent segments. So point B right here is the midpoint of this segment AC. And the way we know that is because of the geometric code right here, this tick mark and this tick mark. Those single tick marks mean that those 2 segments are congruent to each other. And if those 2 segments are congruent, then their lengths are equal. So I'm just going to make up, let's say that they are 5 feet each. That would mean that the entire segment is 10 feet, putting B right in the middle of segment AC. And that's why we call it the midpoint. And now this line, let me erase that scratch work. This line M, it is bisecting that segment AC. That means that it is cutting it into 2 congruent parts. Okay, it's called a segment bisector. Just think bisect. Bi for 2, section, so it's dividing it into 2 equal parts. And it doesn't matter that the segment is kind of tilted. If it was tilted this way or this way, it doesn't have to be perpendicular. As long as it cuts or intersects the segment at its midpoint, then it cuts it into 2 congruent parts, making it an official segment bisector. All right, let's use the segment addition postulate to work through a problem here. It says that if MP equals 47 units, then find MN and NP. All right, if I am able to easily add stuff to the figure, I like to do that. It's valuable to me to see it all in one place. That way I'm not trying to memorize it or just picture it in my mind. I'd rather just be kind to myself and just write it on the figure whenever I can. That way all my information is in one location. Okay, so now we are being asked to find the length of MN, so this length here, and the length of NP, so this length here. And all we know is that MN is represented by the algebraic expression 5x plus 1, and NP is represented by the expression 11x minus 2. If we could find the value of x, that would be good. We would be able to move forward and find those lengths. Well, if we're able to write an equation with an x in it, then we can solve that equation for x. So the segment addition postulate is going to set us up for writing that equation. The segment addition postulate says that the length of MN plus the length of NP is equal to the length of MP. So now let's substitute those algebraic expressions and the 47 into our equation. So MN is 5x plus 1, and we have a plus sign. NP is 11x minus 2, then we have an equal sign, and MP is 47. What you guys just saw is translating from a geometric figure to an algebraic equation. This is a very valuable skill that's going to help you get through geometry. We are often tasked with, given a geometric figure, can you translate it into an algebraic equation? The reason we're tasked with that is because if we can do so successfully and we only have one variable in our equation, we can solve for that variable and we can find missing measurements. So let's do some algebra work here to solve for x. 5x and 11x combine into 16x, plus 1 and minus 2 combine into minus 1, equals 47. Now that was all combining like terms. Now let's use the addition rule of equality to add 1 to both sides. And then we'll use the division rule of equality to divide both sides by 16. We've now isolated our x, and 48 divided by 16 is 3. All right, once we have our unknown of x, we can plug that back into the equation and find all the missing parts. So let me erase my work there. Here is that equation solved a little bit nicer. Let's see, we get x equals 3. Then use the value of x to find mn and np. So mn, you substitute the 3 right there, giving you 16 units for this segment. And then NP, you substitute the 3 in right there, giving us 31 units for that segment, making the entire segment, just checking my work here, 16 plus 31, it does in fact equal 47 linear units. All right, let's try an example about midpoints. Point C is the midpoint of segment AB. Find AC, CB, and AB. All right, so it's similar to the last one, except the last one told us the whole length to be some value. So we were able to go this segment plus sign, this one equals the whole thing. But that is not the case here. They didn't tell us the entire length, so we can't use the segment addition postulate of this plus that equals the total length. So we have to come up with something different. Well, we know that the definition of midpoint says that it cuts a segment into 2 congruent parts. And we know that 2 congruent segments have the same measure. So translating this into an algebraic equation would look like this, setting segment AC equal to segment CB. And there are 2 ways you guys should be able to come up with that as the way to start your algebraic equation. Number 1, by definition of midpoint, but also if you look at the geometric code right there and you see that you have 2 congruent parts, you can always set whatever expressions represent them equal to each other. All right, so substituting our 8x minus 6 for AC and our 7x plus 3 for CB, we can then solve for x by adding 6 to both sides. And subtracting 7x from both sides, and we get x equals 9. It is very tempting to stop right there at x equals 9, because in algebra classes, a lot of times that is where we stop. But in this class, and well, all your classes, do make sure to answer the question. And the question wasn't to solve for x. The question was to find AC, CB, and AB. So we need to use our knowledge that x equals 9, plug it back in right there to find AC, right there to find CB, and then we can add those two together to find the total length of AB. Let me erase my work, and I'll show it to you here typed up. All right, substituting the 9 back in tells us that AC is 66 linear units here. Substituting the 9 back in tells us that CB is also 66 linear units, which it should be. If you got something different, you'll have a red flag here knowing you made a mistake, because the segments need to be the same measure based off of this geometric code and the definition of C as a midpoint. And if we take our 66 plus another 66 units, we have the entire length of AB. Now this is using the segment addition postulate right there, and we end up with a segment that is 132 linear units. And that will conclude our discussion on section 1.4. My name is Jamie Emigh. Thank you for joining me, and I will see you next time for our discussion on section 1.5.